Yeah, greetings to you all, especially those up there in the Olympus. May the gods protect you. Okay, so yesterday, if some of you were there, I talked specifically about the 40-year journey, and I'll have one summary slide next to basically show you what it took, how much luck it took over 40 years to push oneself closer and closer to one of the possible candidate massive black holes, namely the one in our own galaxy. I'll come back to this today for some of the very exciting news things which I didn't have time yesterday. But today I will actually emphasize more the broad picture. The broad picture of how galaxies formed, grew over cosmic time, what we know about this at this point, and how the black holes fit in there. Who ordered them? Why? What is their role in the evolution of galaxies? So in a way, what you see today is a broad panoplia of astronomical, observational, and theoretical work, because these kinds of studies, which I will talk about today, require looking at very many different wavelengths. So not only the near-infrared, but also, as you see here, the millimeter, sub-millimeter go into space, the Hubble Space Telescope, of course. On the left side, the Herschel ESA far-infrared mission, which was very successful, but only short period of time up there because of the cryogenics running out. And then telescopes which are now beginning to produce science, which is on the bottom right, the James Webb Telescope, a very sensitive telescope to look at the mid-infrared wavelength range. And then on the upper right, the thing which many of us, including my own group, are looking forward to next, which is a 40-meter telescope, a 40-meter telescope. So that's, 5 times as large a diameter as the current 8-meter telescopes we're using. You can imagine 40 over 8, 5 squared, 25 times the collecting area of the BLT. So that's going to be fantastic. So the story which I will tell you today in a way is just a report on the way, another journey, going back in time. But let me summarize what I told you about yesterday, which is the story of the galactic center and the many actors in this field, starting, of course, with the heroes of general relativity, Einstein included, Roger Penrose also, then Donald Lindenbaum, Martin Rees, and then Charlie Townes, who started this game in the 1960s and 70s in astronomy. Up to that time, black holes had been a pure mathematical, not fiction, but at least subject, which most astronomers didn't care much about. Roy Kerr, who was one of the actors in the 60s and found the Kerr metric, basically told me once that, he never talked really to astronomers until the quasars were discovered. And I gave you that story yesterday. And then came the gradual picking up of techniques to look at the center of our Milky Way, the radio emission, the radio source, Sagittarius A star, very compact radio source. Then the gas motions, which gave the first indication of that there was something massive in the center. Then the stellar cluster discovered and the motions of the stars measured ever better, until we had now ultra-precise measurements of orbits of many stars. Incredible, because, it zips around in the galactic center. Every night there's action in the central square of the galactic center with stars moving at, about 3% the speed of light there. And from this information, as you move to the right, we can then over time get an ever more precise picture of what's in there and whether what is in there, namely a compact mass of 4.304 million solar masses, is truly a black hole. And yesterday I showed you that we are at a point where we can certainly say, and that was confirmed by the Nobel Foundation, that we have evidence here for a massive black hole beyond any reasonable doubt. And then, as I mentioned yesterday, whether or not you personally, as a physicist, believe in that is a bit your decision, because in science, in physics, we can never say we are done. And in general relativity, we cannot say we are done, because some of the predictions of general relativity are awesome, but also awkward. The central singularity, for instance. Does that really exist? Or if we have a quantum theory of general relativity, we will then find that singularity actually is finite, is finite density. Likewise, the event horizon. Is there any way to beat it? Can we see the possible quantum fumes of Hawking radiation at some point to find the information inside of the black hole, which should be there encoded because of the conservation of quantum numbers. So all of this is something for the future. We've reached an intermediate stop, and I told you that it's not just the way we've done this in the galactic center. There's also techniques using photons in the millimeter range with worldwide very long baseline interferometry in the radio, and then gravitational waves. And I told you that in terms of the gravitational waves, I personally feel that the ultimate experiment to prove the no-hair theorem, which is that black holes really only have 2 or 3 quantum numbers, so to speak, the mass, the spin, and then the charge, that this is really true. We want to show that. That's our job as physicists. Since I can't do that anymore, it's your job. Okay, you up there in the Olymp, you should do this. Okay, so that's my story from last time, so I don't want to repeat on that. But now talk first a little bit about the evolution of galaxies, what we know about this. Then I turn back to the galactic center and talk about some of the rather incredible properties of the central star cluster, which we have uncovered as we were looking at the central region of the galaxy. So in the 1960s, 70s, people started also thinking about how galaxies would form. And early evidence from optical spectra of nearby galaxies by Lindenbell, Egg, and others basically led to the conclusion that perhaps in the early universe, clouds of baryonic material all of a sudden collapsed in what was then known monolithic collapse to form, galaxies very suddenly. That was the belief system in the 1960s, but then when ever better telescopes became available, when optical astronomers started looking at the distant skies, there were no relics. What they found were, what we now would call measly little objects, and moderate redshift of 0.5 to 0.8. So that's, in terms of look-back time, a few billion years. Certainly nothing in the very more distant past, which was very bright in the rest frame, ultraviolet. At the same time, of course, cosmology, theoretical cosmology, led to the conclusion that cosmic structure on large scales was controlled by dark matter, and that the underlying dark matter particle, if it's really a particle, had a lot of mass. So it was not relativistic in the early universe. And as a result, you would expect the buildup of dark matter structure in the early universe over time from small to large through constant merging of structures. I'll come back to this at the end of the talk in terms of modern simulations. So in this framework, which was there pretty completely in the 1990s, and awaiting the space telescope, the Hubble Space Telescope's first pictures, one would not have expected much past activity in terms of this monolithic collapse. So then people took those pictures, and not only with the HST, but also with infrared techniques, with the infrared satellites, and also looking at the black holes. All of this is sort of put together here in a summary slide in terms of the star formation activity averaged over volume per volume as a function of redshift increasing to the right, or also look-back time increasing to the right. So on the very, very right, 13.76 billion years ago is the Big Bang. And then you see that there was as you go back in time, an increase by about a factor of 20 from current epoch back to about 10 gigayears ago of the cosmic star formation activity. So a Milky Way mass galaxy would have formed 20 times many more stars than today. Our Milky Way is a moderate to large disk galaxy, as we say, star-forming disk galaxy of almost 10 to the 11 solar masses in baryons and 10 to the 12 solar masses in baryons plus dark matter, and forms about 1 to 2 stars per year now. Back then, it would have been, 30, 40, 50, maybe even up to 100 solar masses per year. You will see more about this in a few minutes. So this peak of cosmic star formation activity tells us there was something special going on at that period. And what was that? We now believe that this is due to the fact that when the universe expanded in the early universe, it took a while until local overdensities in dark matter stabilized the expansion and started to collapse and form what we now call dark matter halos. And in these dark matter halos, basically you have potential wells of gravity within which then baryons, which are far less frequent and abundant, fall in. And then because normal baryonic matter also sees electromagnetic interactions and not just gravity, you can actually then start to transfer angular momentum very efficiently. And so the baryonic material then settled in the cores of the dark matter halos and formed galaxies. And that seems to have occurred very efficiently 10, 11 gigayears ago, forming very luminous structures. And at the same time, you see that green and bluish line. That's sort of the same kind of a story now on the quasars. So we can see quasars in X-rays and radio and also in the infrared. And these active galactic nuclei also were more abundant in the early universe. Same story, pretty much the same peak. So there was a symbiosis, if you like, of the star formation activity of galaxies and that of central black holes. And we would like to understand, of course, why that was and how it was. When then HST started getting pictures around 96 to 2000, these were the pictures HST would report back in the rest frame ultraviolet, optical frame pictures. Now these very, very asymmetric, clumpy, strange objects do not look like galaxies we have in the current universe. The beautiful, serene disk galaxies, spiral galaxies, or the elliptical galaxies, which are passive, don't produce much star formation. These things are very compact, clumpy, as I said, don't seem to show any kind of a structure which is regular and would point towards rotation or anything like that. So these clumpy star-forming galaxies, wow, what could they be? Well, the answer was pretty obvious. I gave them to you already. If you have mergers, collisions between galaxies, then you can transfer angular momentum very efficiently and collapse to more compact structures. So the picture, going along with the dark matter picture, which I discussed, was what you see here are the products of galaxy-galaxy mergers, 10 gigayears ago, and that then led to these clumpy, very bright things with a lot of luminosity. If you look at the typical luminosity of these galaxies at the peak there, it's about 10 to the 12 solar luminosities if you take into account also the infrared bands. And that is a luminosity class which you do not see in the local galaxy system either. And you can get that in such collisions. In the local universe, we see such mergers very rarely. But when they do, of course, in a hurry, you drive material inwards and then you get a lot of star formation. We call that bursts of star formation. In that burst, typically lasting 100 million years, you can reach these star formation luminosities, which is equivalent to about 100 solar mass per year star formation rate. But now, slowly it became real from simulations that this major merger frequency is actually not so high, because galaxies are far apart from each other, even in the early universe. It's sort of once every few gigayears. So if you think about this a little longer, on the one hand, if you look at the observations of these galaxies, the mass doubled every few hundred million years in stars at that time. Yet only every few gigayears you would have such a collision. Is that sufficient to explain this luminosity? That was the question. Let me just give you one example of current research of great excitement for the black holes. So far, the black holes at high redshift we only can see through their luminosity action. Okay, we can see how much radiation they produce in X-rays, in the ultraviolet, and in the radio, and make models of that radiation. With gravity, which you already heard about, which is interferometry in the near infrared, we can now, for the first time, actually go into the cores of galaxies which you just saw at the peak of galaxy formation and measure the activity and resolve the spatial activity of gas near the central black holes. So here is a galaxy observed for the first time this year with gravity at redshift 2.3. So that's 10.8, 11 gigayears ago. And we look at, on the left side, H alpha here. And the H alpha has these broad wings, few thousand kilometer wings. They're very well known in local galaxy AGNs. And that's called the so-called broadline region. And the broadline region, empirically we've learned, is hot gas around the central black hole on a scale of about a parsec, a little less, and basically acting on gravity. And so when you measure the motions, if you resolve the broadline region, you can measure the black hole masses. And that's what you see there in the center. That is, I would say, a real triumph of experimental work. You see there that the instrumental phase of the interferometer changes across the spectral line. And that's what you would get if you have a broadline region which is rotating. Because then, of course, on one side of the black hole, the gas comes at you, and the other side, it goes away from you. So you can make a model here, which you see on the right side. This is very well fit by a rotating broadline region of a sheer incredible compactness, 0.2 parsecs. Okay, so that's less than 1 light year at redshift 2.3. We can measure the mass of the black hole to be 10 to the 8.3, 2 by 10 to the 8. We can measure other properties of this central region. So over the next years, I hope we will actually go ahead and study, so to speak, in detail, the mass distribution and the evolution of these AGNs at high redshift. Let's go back to the galaxies. In about 2005 to 10, both HST and ground-based big telescope work was starting to look in more detail at the distribution of the light of these early star-forming galaxies. And so the plots which you see here are at different redshifts. So there's redshift 0, the modern universe, 0.5, 1, 2, so going back in time. Then you see the horizontal axis is stellar mass, and the vertical axis is star formation rate. So that's the quantity we looked at before in an average sense. Now we look at it galaxy by galaxy. And what you see is that at all these redshifts, the star-forming population, which is this population here, falls along approximately a linear relation. Let's not get into much detail of any deviations, approximately a linear relation. The star formation rate is the bigger the stellar mass is. Now that's not what you would expect if all you see here are starbursting mergers. This looks much more regular, right? The bigger the body, the more activity is. That's what this says. And so this looks like a much more serene, equilibrium type picture. And you notice there is this dashed line here, which is basically the line of this this linear relationship at redshift 0, and you go to higher redshift, 0.5, 1, 2, and you see that the galaxies which are observed in this linear relations are always higher, ever more high. That's the same as what I showed before, that as you go back in time, per average volume, the star formation rate increases. So here we see that this has to do with all galaxies having more star formation rate. So we now call this linear relation the star-forming main sequence. You also notice there's something below that. So massive, but very little star formation rate. These galaxies we call in the local universe passive galaxies. So they don't form much stars, and often are elliptical in nature, elliptical galaxies. So they're not disk galaxies rotating, but they are sort of other beasts. Now, going back in time, you see that the prominence of this population of passive galaxies is decreasing. So by redshift 2, yeah, there are some, but not many. So that gives you a first hint that galaxies form, then they form stars, and at some point in their lives, they transit into this passive sequence. And then there's a clear process, or processes, I should say, which make that transition. Now, as to this merger story, the pictures which HST had sent in 96 to 2000, which I showed you, were pictures in the rest frame ultraviolet. Now, the red ultraviolet light is affected strongly by dust. And over time, it became clear from infrared measurements that galaxies at high redshift are extremely dusty. Not expected. Also, a lot of interstellar cool material, also not expected. And so if you correct for this extinction by using multi-band observations or even infrared observations and plot now one of these plots here, like here, but now not with the star formation rate, but with the shapes of galaxies, of course. Now here you can only put on a modest number. So there's the main sequence right there. And when you look at these objects there, they're fairly regular once you correct for extinction. There's a nuclear region, a central bulge, especially for the more massive ones, and then they're sort of roundish or elliptical, just like modern galaxies. So that picture, the snapshots from HST early on were misleading because you were looking at a band which was heavily affected by dust extinction. So once you correct for that, the picture looks totally different. In fact, in the next stage, when one used integral field spectroscopy on the big telescopes, you could now look at the motions within these galaxies in H-alpha, but also in the millimeter range in CO. And so what you see here are, again, the main sequence, and then you see individual galaxies here. It's very crowded, I apologize. And the colors is basically a measure of the velocity of the gas along the line of sight. So red means receding from us. Blue means approaching to us. And you see most of these galaxies are fairly regular, blue on one side and red on the other, and a transition in between. Well, that's the very well-known characteristic of rotation. Right? If you have a rotating galaxy at some inclination, then the galaxy will move towards you on one side and away from you on the other. So we've learned all of a sudden that once you use techniques which make you independent or less dependent on extinction, these galaxies do look fairly regular. They're not mergers. They're disk galaxies. Disk galaxies, and we are now able to say from samples of thousands of these objects after about 15 years of study that more than 70% of the star-forming population of these high redshift galaxies are rotationally supported disks. They are not like the Milky Way. They're not as thin. They're puffed up. And we believe that puffing is due to the high energetics in these high objects. But it's really clearly these are disk galaxies, serene like our modern galaxies for most of the time. Now, mergers do occur, but not so frequently. Now, this is now a snapshot or a story which is spanning about 25 years. What are we doing now? Well, we are pushing this now to a higher redshift. With the James Webb Telescope, discovering new objects at redshifts beyond 3, 4, 5, even up to 10. So that's not anymore 10 gigayears ago, but 12 gigayears ago. About 1 and even less than 1 gigayear after the Big Bang. And so the question, of course, is when did this start and how did it start? And was it always the same story, or as we go to the highest redshift, we all of a sudden see other things emerging? Wait, let's tune in and see how it will come out. Now, what then causes the star formation rates to be so large? Is it that these galaxies, endowed with some gas, like our modern galaxies, form stars more efficiently and therefore have higher star formation rates? Or is it they just have more of it? So that was a very open question, and this merger picture, which I told you was sort of the starting point of all of this, would have favored the former. Because in a merger, you compress gas clouds very efficiently, and then you might form stars very efficiently. Star formation in modern molecular clouds in the Milky Way, very inefficient process. It's about only 1% of the gas in a cloud at any given time is collapsing to stars. And the reason why that is believed to be because molecular clouds are very dense on average, but they're also very turbulent. So the turbulence prevents gas from collapsing everywhere, excepting in a few spots. Is that the case at higher redshift, or is it maybe different? So what has done, and what we have done, in fact, is then to measure the molecular content of these high redshift galaxies as a function of redshift again. So redshift 2 is here, redshift 1 is here, 0 redshift is here. And we measure this quantity here, which is called the depletion timescale. So that's the ratio of the mass in molecular gas divided by the star formation rate. So that is a measure of how fast a galaxy is consuming its fuel for star formation in time. So a small depletion time scale is high efficiency star formation. A large depletion time scale means low efficiency. So if the model is right, that high redshift galaxies are mainly more efficient star-forming emitters, you would expect this depletion time to rapidly drop. And the answer is, it does drop, but not rapidly. And surely not by the factor which the star formation goes up, which was a factor of 20, as I told you. This is a factor of a few. So what is it then? The answer is, it's the amount. So if you plot not the depletion time, but the fraction of material relative to stellar material in molecular gas as a function of redshift, you see that goes up by a large factor. So the reason why high redshift galaxies formed stars so efficiently on average is because they had much more interstellar molecular gas. And why would that be? Why would that be? Now, the answer seems to be because in the high redshift universe, because the universe was more compact, the flow of gas into galaxies from the dark matter halo and the intergalactic component was much, much, much higher. Because, so to speak, in the early universe, there was more gas and it's more compact. Now, let's go back now and jump back to the galactic center and look at some of the issues there, which I discussed last time. So yesterday we discussed how we observe stars remarkably close to the black hole, which is this dot here on highly elliptical orbits, some of them with orbital periods of 10 to 20 years, which is astounding, and high velocities when they approach the central black hole near Perry here. And this being our most precise tool to measure the black hole mass. But now let me turn this question around and say, what have we learned about the stars? Okay, that they're there for us to use them as a tool is fantastic. Thank you, nature. But who ordered this? Did you expect this? Absolutely not. Absolutely not. The theoretical story is that when you have a black hole, then yes, it accretes material, including stars. So you would expect after time, so to speak, a star cluster being there, which is very concentrated, and toward the center forming a so-called cusp. I come to this next. But surely not star-forming material, because the tidal forces from the central black hole are so fierce that it prevents the formation of stars near the black hole due to tidal forces in the gas clouds. And that's a process which is so efficient that within, say, half a parsec or 0.1 parsec of the galactic center, you surely couldn't form stars. Now, this particular star is only about 10, 20 million years ago, old. So at this point, or this point, or that point, you cannot have formed it. Yet it's young. So who put it there? All right. So let's talk about that question. So the theoretical prediction in the 1970s by Bacall and Wolf and others was that if you calculate the average equilibrium state of a star cluster around a black hole, if you have infinitely long-living stars, then you get a cusp, which you see here, which in density space, density versus distance, has a dependence on radius with r to the minus 7 over 4 if you have a single mass. Or in surface density, which is what this is, it's r to the minus 3 over 4. So that's the prediction. So what do we see? So when we were able with adaptive optics to look at the central star cluster, and we averaged everything together, all the stars, then we found something which was actually pretty close to a Bacall-Wolf cusp. Check. Nah. Because in this Bacall-Wolf cusp picture, it takes stars to go from here to the central part of the cusp in about 5, 6 gigayears. But the stars we were looking at have an age only of 10 to 100 megayears. That's a factor of 1,000. So they have no right to be there because they couldn't in their lifetime get there through the processes which were thought to be at place here, which is the so-called non-resonant relaxation between two stars which see each other from time to time and then exchange energy and angular momentum with each other. So that doesn't work out, and it got worse. Once we were able to basically tag the stars in terms of stars which are young and massive and old and so forth, then the picture got catastrophic in that, yes, the old stars, the very old stars, the very young stars, with the blue ones here, are cuspy. These are the ones for which we measure orbits. Yet the old stars, here are the red ones here, they're pretty flat. And in fact, even worse, if some of the old stars of more mass, which are these cyan pictures, they actually have a hole in the center. Heck, what's going on? So the picture emerged that there are other processes than this non-resonant relaxation which come in here. The non-presence of central massive giants is perhaps because in the central region, the density is so high that stars are colliding and destroying each other. That was the idea. And for the young stars, we didn't know. How could they have come in there in their lifetime? Again, the non-resonant relaxation parameter in the galactic center is gigayears, whilst the central stars here have lifetimes which are much, much shorter than this. So collisional destruction of giants was one of the proposals. Then that there are timescales which are much shorter than the non-resonant relaxation. And we now are beginning to have an idea that in this very complex interplay, in fact, you can perhaps understand these young stars. So for instance, if you look at the youngest and most massive stars in the galactic center, the O and Wolf-Rayet stars, there is a population of about 150 such stars, which obviously lives on an inclined disk. So they're actually rotating. They're rotating in a fairly regular fashion. So in other words, if you project the component perpendicular to this rotation, you get a very well-defined angular momentum location on the sky. So that's how a disk looks like in angular momentum space. So if you go at different radii in the galactic center here, you discover there are slightly different populations of these O and Wolf-Rayet stars with different orientations, but all of them pretty regular. It's not easy to measure, and it took, about 10, 15 years of the two groups doing this to get a picture where they all agree. Certainly, we all agree on this inner disk here at around 0.05 parsec. But now, if you plot the distance from the center, the Perry distance from the center, versus 1 minus the eccentricity. So stars over here are highly eccentric. Stars over here are basically in circular motion. Then you find that at larger radii in the galactic center, the stars are at low eccentricity, but they're red, meaning they're very, very luminous, therefore very young. And when you come close to the center, then you find stars which are highly elliptical. So there seemed to be a trend, a very clear-cut trend, that the more massive and the more regular rotating galaxies are further away, while the ones in the very center are all, zipping in there and zipping out there. That's a very important, hint. And the belief we now have how the regular rotating O and Wolf-Rayet stars came about is a falling in of a gas cloud. So here you see a simulation of that. So the gas cloud falls in, the tidal is disrupted initially because of the density being too low. And as you see in these 4 time steps, falls into the center and then shocks on itself, gets very hot, but then also very dense, cools down, and then it can locally form stars in a hurry. And these stars then would be, had an angular momentum very much as the average angular momentum of the infalling cloud. So you get here sort of a disk-like structure which is rotating. So that's the picture we now have. And the alternative of making this in spiral with a star cluster is now considered to be not efficient enough and not fast enough. Now, it's also interesting that if you look at the distribution of masses in these O and Wolf-Rayet disks, then they are top-heavy. The more massive stars are much more frequent than in the local solar environment. And that probably has to do with the fact that here you have such extreme conditions that, when you form a star, then you form it extremely rapidly, but not otherwise. And so that may favor the formation of massive stars. So that's the current story of these O and Wolf-Rayet stars. What about these B stars, the ones we use for our wonderful measuring of the masses? Well, there, the weird proposal came already fairly early on in the late 89 by John Hills, who basically said, suppose you have a binary star, which happens to be on a near parabolic orbit. Parabolic means you basically go into the black hole and almost collide with the black hole. And so the velocity of the binary increases, of course, as it falls in free fall, and such that the initially bound binary system, as you go inward, becomes unbound because, of course, now the kinetic energy of each of its members is larger than the binding energy of the two together. So when they come close to the central black hole, you get a three-body interaction very quickly where energy gets exchanged between that binary and that binary, and one of the binary members gets ejected out of the galactic center, in fact, out of the Milky Way. The estimated velocities are thousands of kilometers per second, while the other one gets stuck. So that picture, this Hills picture, is how we believe the S-stars might have formed. And you can actually calculate, that the kind of distances we see S2 and the other stars in the galactic center would fit with these kind of binaries which have initial semi-major axis of a fraction of a parsec as we see them in the field. And then the capture ellipticity of the captured star is very high, a little higher even than the ones observed. Whilst the other star, the hypervelocity star, as I say, leaves the Milky Way, and these stars are also observed now. So I would say that picture looks pretty good. There's some details which may not fit quite well, and it explains why, as I showed you, near the black hole there, all the stars on these highly elliptical orbits. That's due to the nature of this process. I don't want to go into the details here. As I said, there's still an ongoing field where people, unearth new pieces of evidence and look at alternatives. Okay, yesterday I showed you this graph at the very end, where I said after 40 years we had been able to come from a distance of a few parsecs where you begin to see that the mass is dominated by a central mass, inward, always seeing the same mass of 4 million solar masses, and showing that very else is there. And then, of course, in the very center, you have the near event horizon structure, which you can see with the event horizon telescope in this beautiful picture of the shadow of the black hole, and then the gas. Now let me add a little bit more to this by showing you how much we have actually learned in the last year about this green stuff, this hot gas, which is very close to the black hole on scales of a few times the event horizon size. There, I guess I eliminated. There, basically, we can measure the motions of the gas as well as the polarization, and find that the gas is moving on these near circular orbits and totally polarized, such that the polarization follows them. And the picture is that this occurs when hot gas gets energized by a large factor in magnetic reconnection events in the very center, and then for a while basically emits synchrotron emission, and in that process we see this. And so it becomes a very precise tool of the motions in the central region. Okay, let me finish up by going back to the large-scale picture. So I've told you empirically we found that as you go back in time, the activity in star formation increases, as does the activity in AGN. I've told you that most everyone would accept that the AGNs are highly accreting black holes, and the star formation largely is due to accretion of gas from large scales. And the remarkable thing is that when you plot the mass of the central object, let's call it the black hole, which we can, of course, not prove in every one of these galaxies. We can, to some extent, in the galactic center, but not in the other galaxies. But assume that the galactic center basically is enough of a proof that we can accept it for the others. And we plot that against the mass of the central bulge, or in the case of an elliptical galaxy, you can actually take the mass of the entire galaxy, then there's a correlation. It's scattery, but about 0.2% or so of the mass of a galaxy seems to be in black holes, in a black hole, I should say, in the center. Now, at the distance of the bulge, the outer bulge, so that would be a few kiloparsecs, the mass is completely dominated by the galaxy and the stars. So, the central black hole dominates only about 1 parsec in size. Outside, it's all dominated by the star cluster. So I always say the black hole in Andromeda knows it's in Andromeda because gas is accreting from Andromeda into the black hole. So if you paint it green, the black hole in the Andromeda will report only having recently seen green stuff. But the stars in the bulge of Andromeda don't know that there's a black hole, because the black hole in Andromeda is not active. And the activity in galaxies is rare, at least in the local universe. So why should they know of each other? Yes, they do. So when that plot was first shown in the end 90s, people immediately said, oh, this points to the past. This points to a process in the past where the two knew about each other. So let's go into the past. There we are. And as I already indicated, when we go to the past, both the star formation activity and the AGN activity increase, such that we have this prominent peak which we discussed. And the picture is exactly what I sketched for you. Here you have your black hole and the galaxy around, and all of it is controlled by flows from the outside. So when gas streams at high rates into the central galaxies, starting more active star formation, then some of it also trickles down to the central black hole. So in this picture, at least over long periods of time, you would expect a co-evolution, both grow at the same time. Now it's more simple, more difficult than you think, because if you now go ahead and look at AGNs only, and then look at the star formation rates, so you pick one of them, and then you look at the properties of the other, what you find there is no correlation. So the picture is only true, this co-evolution is first of all only true on average. And on the small time scale, there will be huge fluctuations. Sometimes the star formation rate dominates, sometimes the black hole. And of course, during those periods when there is a quasar being fed, well then all hell breaks loose. So one has to be a little careful with the conclusions. So Jan, of course, has asked several times already, what was first? Who started it all? We don't know. We have to find out. That's the job of the next years, quite obviously. So let me show you at the end a state-of-the-art simulation from the Fokker-Springel group. So what you see here in blue is the dark matter structure. The expansion of the universe has been taken out, so it looks as if it's not expanding. But you see immediately that as time goes on since the Big Bang, which you see on the lower left, the structure gets ever more visible. Filamentary structure, which we call the cosmic web. And then at the crossing points, etc., you see dark matter halos forming. And then in these dark matter halos, you see now red colors appearing. That's star formation. So star formation is triggered by the formation of large-scale structure. And so then the galaxies grow, and then they start exploding, as you see here. That's due to the effects of supernovae in the galaxies as well as black holes. So by 3 billion years after the Big Bang, that's exactly at the peak of this galaxy formation activity. You see, my God, bang, boom, all over the place. Okay? So that tells us that this peak of galaxy formation as well as AGN activity was triggered by the formation of large-scale dark matter halos at this epoch for the first time. So the two are correlated. And when then AGN activity becomes as intense as a quasar, well then the galaxy may be forced to transit from the star formation sequence down to the passive sequence, just because all the gas is being blown out. Pretty violent, is it not? That's our universe. Thank you.